A pedestrian standing at Charing Cross in the centre of Bendigo sees a wide intersection of 19th-century civic architecture. Solid brick shopfronts, the cast-iron tiers of the Alexandra Fountain, stone facades along View Street, and traffic moving between ornamental street plantings. The bitumen is level. The foundations of the post office and the municipal buildings sit square and undisturbed against the footpaths. Beneath this single provincial intersection lie more than 5,000 kilometres of underground mine drives and thousands of abandoned vertical shafts. The city of Bendigo was not built adjacent to its goldfield. It was surveyed and laid out directly across the surface of the richest quartz reef gold deposit in the country. What is remarkable is not simply that the ground was hollowed out down to depths exceeding 1,000 metres, but that the entire urban surface grew, stabilised, and went about its modern civic life as if the solid earth beneath it had never been systematically removed. For decades, surveyors, municipal engineers, and property owners treated the underground labyrinth as a closed 19th-century chapter, safely sealed beneath road base and masonry. How does a modern city of more than 100,000 residents remain standing above one of the densest networks of abandoned underground voids on the continent? And what happens when the hidden geology begins to move? To understand how this situation developed, it is necessary to examine what the early authorities in Victoria assumed about the ground when the first alluvial rush broke along Bendigo Creek in late 1851. In the initial months of the gold rush, miners worked shallow surface gravels with pans and timber cradles. The government surveyors who laid out the permanent township in the early 1850s assumed that the extraction was temporary and confined to the surface soil. It was an entirely reasonable conclusion for the era. The alluvial gold was concentrated within a few metres of the topsoil, and traditional British mining precedent held that bedrock beneath alluvial plains was generally barren. That assumption collapsed within 3 years. In 1854, miners began tracing the rich gold deposits into the solid quartz reefs that outcropped through the sandstone and slate ridges. The geological structure of the Bendigo goldfield is unique in Australian mining history, an intensely folded sequence of Ordovician sedimentary rocks that formed regular, repeating, arch-like folds known as anticlines. Within these underground arches, silica-rich hydrothermal fluids had deposited gold within distinctive saddle reefs, stacked one above another like nested cups at vertical intervals down through the crust. Once the saddle reef structure was understood by miners and mining engineers, the extraction changed from surface scraping into systematic deep-vein industrial hard rock mining. Between 1851 and 1954, more than 700 separate mining companies operated across the Bendigo field. They sank deep timbered shafts along the dominant reef lines, including the New Chum, the Garden Gully, the Hustler, and the Sheep's Head lines. As the mining boom accelerated through the late 19th century, the surface settlement grew at the exact same pace. Instead of separating the commercial district from the industrial workings, the banks, law courts, hotels, and suburban houses were built directly over the leases. The Victoria quartz mine on the New Chum line eventually pushed its shaft to a vertical depth of 1,404 metres, making it at the time one of the deepest excavations anywhere on Earth. By the turn of the 20th century, mining syndicates had driven horizontal tunnels, crosscuts, and stopes underneath the very streets carrying horse-drawn trams and brick sewer lines. When the deeper operations gradually became unprofitable due to water pumping costs and were finally abandoned in the mid-20th century, the headframes were dismantled, the surface portals were covered over with timber or concrete caps, and the records of thousands of smaller prospector shafts were lost to private family collections and forgotten municipal registers. The surface was levelled, asphalted, and handed over to ordinary urban expansion. To understand how thousands of kilometres of subterranean voids were hollowed beneath Bendigo, the investigation must step back roughly 440 million years into the geological record of eastern Australia. During the Ordovician period, this entire region sat beneath an ancient ocean off the eastern margin of the Gondwana supercontinent. Turbidity currents flowing off the continental landmass deposited massive thicknesses of alternating sand and mud across the ocean floor. Over millions of years, these marine sediments compressed into dense turbidite layers of sandstone, siltstone, and black slate. Then came the tectonic collision. During the Benambran and Taberaberen orogenies, immense crustal compressions squeezed these horizontal marine layers from east and west. The rock strata did not simply fracture, they buckled into a dense series of upright, accordion-like folds stretching across the central Victorian goldfields. This crustal folding created the defining structural feature of Bendigo, symmetrical anticlinal arches and synclinal troughs repeating at regular intervals across a corridor roughly 8 kilometres wide. As the rock layers bent under intense tectonic heat and pressure deep within the crust, slippage occurred along the bedding planes. Gaps and fractures opened along the hinge lines at the crest of each arch. Deep within the crust, superheated hydrothermal fluids enriched with silica, sulfur, and gold migrated upward through deep regional faults, filling the structural voids at the crests of these folds. When the fluids cooled and crystallized, they formed quartz saddle reefs. The structural geometry was unprecedented. Instead of single vertical veins, the gold-bearing quartz formed recurring arches stacked vertically beneath one another like nested layers along each fold axis. For hundreds of millions of years, continental weathering eroded kilometers of overburden, exposing the upper crests of the saddle reefs to the surface. Aboriginal peoples of the Dja Dja Wurrung Nation, the traditional owners of Geelong and the surrounding Bendigo region, managed this country for tens of thousands of years, navigating a landscape where exposed quartz outcropped along low slate ridges and creek valleys. When colonial prospectors discovered gold at Bendigo Creek in late 1851, the easy surface deposits masked the complexity of what lay beneath. Early surface miners operated under Victorian mining laws that granted tiny individual claims measuring only roughly 8 square meters. Prospectors sank thousands of shallow, unrecorded circular and rectangular shafts straight down through the clay and weathered slate to reach the gravel layer, abandoning them as soon as the surface yield dropped. By the 1860s, the nature of the deposit forced a complete restructuring of mining tenure and technology. Individual prospectors were replaced by registered joint stock mining companies capable of funding Cornish steam pumping engines, heavy timbering, and industrial explosives. The Geological Survey of Victoria, led by pioneering geologists such as Ferdinand Krauss and later E.J. Dunn, began the painstaking work of mapping the subterranean saddle reefs. Dunn's systematic structural surveys between 1892 and the early 20th century established that the Bendigo field contained over 30 distinct anticlinal lines running parallel to each other in a north-northwest orientation. To extract the gold from these stacked reefs, mining companies sank vertical timbered shafts directly through the crests of the anticlines, driving horizontal levels and crosscuts every 30 to 60 meters down into the rock. Between 1851 and 1954, an estimated 700 individual mine shafts penetrated the Bendigo field, producing more than 690 tons of gold from both alluvial and hard rock sources. As the gold output peaked, a secondary transformation occurred on the surface. Bendigo was not abandoned like a typical boomtown. It grew into a permanent, prosperous regional city. Grand Victorian-era commercial institutions, schools, water reservoirs, and residential suburbs were surveyed and built directly across the surface footprints of the mining leases. When the deeper shafts gradually closed down in the decades leading up to 1954, the mining companies ceased active dewatering, removed their winding gear, and capped or backfilled shaft openings using whatever materials were immediately available: timber logs, loose rock mullock, and thin metal sheets. Decades of urban development buried the surface evidence of this massive extraction beneath roads, parks, and housing estates. But while the headframes and battery houses vanished from the surface landscape, the vast network of stopes, drives, and unmapped shafts remained intact in the dark bedrock beneath. What happens when groundwater, chemical weathering, and surface weight begin to act on a subterranean void that has been forgotten for generations? For nearly 4 decades after the last major commercial operations closed, the subterranean extent of Bendigo remained an abstraction. It existed as thousands of individual paper lease plans stored in state archives, separate mining company records, and disconnected municipal maps. The ground above had been subdivided into residential blocks, public parks, and road corridors. Because the surface showed almost no physical signs of the underlying workings, urban planners and structural engineers operated under the assumption that the bedrock was stable. The moment the way of looking at this ground changed occurred in the 1990s. Geoscientists and geotechnical engineers began systematically compiling the historic records into the first regional digital models. The Geological Survey of Victoria, working alongside the Department of Primary Industries, initiated a program to digitize and spatially rectify more than 6,000 historic mine plans, lease surveys, and underground cross-sections dating back to the 1850s. When these two-dimensional surveys were geo-referenced and overlaid onto modern aerial photography and cadastral boundaries, the result revealed an astonishing degree of overlap. Major suburban arterial roads, high-density residential subdivisions, and commercial buildings in suburbs such as Long Gully, Golden Square, and Ironbark sat directly on top of uncompacted mullock, collapsed shallow drives, and unrecorded vertical shafts. The real scale of the problem, however, could not be confirmed by historic maps alone. Many early prospector workings were dug without formal lease surveys, and company plans frequently stopped being updated months before an operation went bankrupt and abandoned a shaft. To map what lay beneath the built-up areas without demolishing the surface, researchers deployed modern geophysical techniques. High-resolution airborne laser scanning, or LiDAR, stripped away modern tree canopies and structures to reveal subtle ground subsidence troughs, forgotten open cuts, and crown-hole depressions following the exact north-northwest strike lines of the underlying anticlines. On the ground, geotechnical teams used ground-penetrating radar and electrical resistivity tomography to image the upper 15 meters of the soil profile. Ground-penetrating radar works by transmitting electromagnetic pulses into the earth and measuring the reflected signals returned from underground interfaces. Where a solid rock mass gave way to an open void, an uncompacted timber cap, or a hollowed stope, the radar profiles registered distinct, high-amplitude hyperbolic anomalies. In residential streets across Golden Square, these scans repeatedly identified air-filled cavities lurking less than 2 meters beneath modern asphalt. To verify the depths of the major workings, geologists turned to diamond core drilling. Drill rigs boring through suburban road reserves struck open voids where 19th-century stopes remained uncollapsed hundreds of meters underground. Downhole logging cameras lowered into flooded shafts revealed intact Cornish timber sets, preserved in low-oxygen groundwater, holding back tons of fractured sandstone and slate. The scientific proof established two critical facts. First, the Bendigo underground is not a series of isolated holes, but a continuous, interconnected hydrological network spanning thousands of kilometers of rock. Second, the stability of this entire subterranean architecture was changing. When the mine stopped pumping, water levels began a slow, continuous rise through the old shafts. What happens when millions of liters of acidic, mineralized groundwater fill an underground labyrinth sitting directly beneath a modern community? The consequences of 5,000 kilometers of subterranean voids beneath Bendigo are no longer confined to historical curiosity. They manifest as active engineering challenges, structural liabilities, and complex groundwater management operations across the municipality. The most direct physical risk is subsidence. When 19th-century miners ceased operations, they frequently sealed shaft openings with timber collars and backfilled the upper sections with loose waste rock. Over decades, underground moisture rots hardwood timbers, and groundwater fluctuations wash unconsolidated fill downward into deep, uncollapsed stopes. The result is a crown hole collapse, the sudden, unannounced opening of a vertical void at the surface. In Bendigo, the Department of Energy, Environment and Climate Action, alongside the City of Greater Bendigo Council, maintains an active register of thousands of abandoned mine features. Every year, ground collapses occur in residential backyards, roadside verges, and public reserves across the historic reef lines. Remediation requires specialized geotechnical intervention. Rather than simply tipping earth into the opening, engineers must excavate down to solid bedrock, construct reinforced concrete caps or polyurethane foam plugs, and install subsurface drainage systems to prevent water from scouring the surrounding soil profile. The cost of stabilizing a single complex shaft collar can reach tens of thousands of dollars, a responsibility that falls across state agencies, local government, and private property owners depending on land tenure. Beyond structural stability, the underground labyrinth has created a major hydrological management issue known as the rising mine water phenomenon. When the deep mines operated, steam pumps continuously extracted groundwater to keep the drives dry, lowering the regional water table by hundreds of meters. When the last commercial pumping ceased in the 20th century, groundwater naturally began to recharge the empty workings. As the water moved through thousands of interconnected shafts and drives, it reacted with exposed sulfide minerals in the slate and quartz, specifically pyrite and arsenopyrite. The resulting mine water is heavily mineralized, containing elevated concentrations of dissolved salts, arsenic, and heavy metals, accompanied by low pH levels and dissolved hydrogen sulfide gas. By the early 2000s, this acidic water had risen to within tens of meters of the surface in central Bendigo. Left unchecked, the water table would have surfaced in low-lying suburban areas and discharged directly into Bendigo Creek, threatening the water quality of the Campaspe River and the wider Murray-Darling catchment basin. To prevent an uncontrolled surface discharge, the Victorian government intervened through a major environmental engineering program. A managed pumping and treatment regime was established at the historic Central Deborah gold mine and New Chum sites. The facility pumps millions of liters of mineralized water weekly from the flooded labyrinth, routing it through an advanced treatment plant that neutralizes the acid, removes dissolved arsenic and heavy metals, and safely disposes of the precipitate before the treated water is discharged. Managing this subterranean water table is not a temporary fix. It is a permanent, ongoing operational commitment required to keep the city dry and its waterways safe. For the modern resident living above the reef lines, the presence of the underground network dictates planning overlays, building foundations, and environmental monitoring. Yet, the physical reality of the voids is only one dimension of how this landscape shapes the present. How does a community reconcile the physical hazard beneath its foundations with the cultural and economic identity that built the city in the first place? The final open line of this investigation reaches beyond modern risk registries and groundwater treatment plants. It concerns how a society chooses to interact with the geological void that created it. At the central Deborah gold mine, tourist cages still descend 61 meters into the upper drives, allowing visitors to walk through narrow, timber-shored tunnels beneath the southern end of the city center. Further north, modern deep exploration drilling continues to probe the deeper folds of the saddle reefs beneath the northern suburbs, where modern gold producers have periodically evaluated the remaining mineralization far below the 19th century workings. What kept the true scale of this subterranean network unnoticed for generations was the administrative boundary of the property title, which recorded ownership across a flat, two-dimensional surface while completely ignoring the three-dimensional geometry of the extracted earth beneath it. For more than a century, cadastral maps treated the land as a continuous plane of lots, streets, and municipal boundaries. As long as the property title showed a solid boundary line, the absence of the bedrock beneath that line was treated as non-existent. The surface was mapped in exhaustive detail, while the underground was left to decay in darkness. Much of the underground record remains genuinely unresolved. While the major company shafts on the primary anticlinal lines were surveyed with high precision by Victorian government geologists, thousands of early prospector shafts sunk during the 1850s were never surveyed at all. These unrecorded shallow workings, estimated by historical mining researchers to number in the tens of thousands across central Victoria, remain completely invisible until a heavy rainfall event, a broken water main, or modern construction loading washes out the surface plug and exposes the void. Geotechnical engineers continue to develop predictive risk models, but complete certainty across every suburban block remains impossible. The modern street map of Bendigo looks solid, settled, and finished. The ground beneath it is an active, hollowed architecture of stone and water that continues to settle, breathe, and demand engineering intervention more than a century after the last miner left the cage. Which forgotten mining landscape or hidden underground feature in your own state or territory has always struck you as the most overlooked? Tell us in the comments below and subscribe for more deep geographical investigations across the continent.